Okay, for equilibrium, okay, we have learned that equilibrium happens, okay, when you have the system being in dynamic condition. What is dynamic? The reaction is going to continue to happen. The reaction didn't stop. The second part is going to be when the rate of forward, okay, equals to the rate of backwards reaction. Okay, and the third one, okay, is going to be when you have, okay, the concentration of the chemicals, reactants and products over there must be constant. Constant doesn't mean same, it's actually they are not changing. Yeah, they are not changing. And then this must happen in a closed system. What is a closed system? Nothing goes in and nothing goes out. So this is important. Now, when this equilibrium system, when we try to make it, let's say, an open system, what is open system? Maybe we remove something, maybe we change something. So there are certain things that we can do. Okay, like for example, I can change the concentration, I can change the temperature, I can change the pressure. Okay, and sometimes I can actually add the catalyst. Okay, all this will disturb, okay, the equilibrium. But when it comes to catalyst, okay, when it comes to catalyst, you need to remember in a reversible reaction, catalyst only increases the rate. But it's very important that you understand that catalyst increases the rate of both forward and backward reaction. Therefore, catalyst just makes sure that the equilibrium is achieved at faster rate. You can actually put it in that way. But these three, okay, concentration, temperature, and pressure, they will affect the position of equilibrium. So the position of the equilibrium, when it comes to that, we need to understand about this Le Chatelier's principle. Now, Le Chatelier's principle, okay, actually mentioned about when a system at equilibrium, when it is subjected to a particular change, the system will shift the position of the equilibrium. Okay, the system will shift the position of equilibrium so that you eliminate the change. Okay, so that you eliminate the change. So how you can do that? Okay, this one we have done earlier. So like for example, if you increase the temperature according to Le Chatelier's principle, okay, you need to bring down the temperature. If you increase the pressure, you need to bring down the pressure. If you increase a particular concentration, you need to bring down that concentration. So we need to actually, we have learned how to apply this. Okay, so I will just roughly go through related to temperature. Let's say if I have A plus B to give me C plus D, and this is going to be an exothermic reaction. And I told you how to remember, just put your hand over there. And this is exothermic reaction. You should feel hot. If this is hot, if you put your hand over here, this is going to be cold. So if let's say this particular equilibrium, you disturb the equilibrium by increasing the temperature. So what is going to happen is you need to, according to Le Chatelier's principle, you need to bring down the temperature. How do you bring down the temperature? By making sure the hot change into cold, bring down the temperature. But when we write down, okay, we tend to write down the position of the equilibrium move to the left. Instead of saying it moving to the left, you can say this is going to be exothermic. So this one must be endothermic. So endothermic reaction is favored. Okay, endothermic reaction is favored. And it is very important to also write down what will happen to the concentrations. Like for example, if you're moving to the left, the concentration of A will increase, concentration of B will increase. But since you're using up the C, using up the D, so the concentration of C and concentration of D, they will decrease. So this is one of the example. Okay, so that is temperature. So let's actually look at concentration. Okay, if I have like this, okay, if I increase the concentration of C, Okay, so according to LCP, Le Chatelier's principle, you need to bring down the concentration. How do you bring down the concentration? By making sure that they react. Okay, so it means the position of the equilibrium will be shifted to the left. So what is going to happen? The position of the equilibrium will be shifted to the left to favor more A, to favor more B, but in that process, C will decrease. So these are the things that you want to actually mention over there. So temperature is done, concentration is done. Let's actually look at pressure. When it comes to pressure, it is very important to remember that it is going to be involving only gas. So let's say if I have this equation and then this is gas, and then there is also C, and that is going to be solid, and it gives me 2D, for example, which is going to be gas. So when I write down, okay, when I want to actually compare the pressure and so on, one of the important things that you need to know is we need to include the gas. So gas, that is solid, we are not going to include. So we are going to calculate the number of moles, okay? We are just going to add. So this is 1, this is 2, so total at the reactant 3 moles, 1 plus 2. At the product, that's going to be 2. So what we are going to have, let's say, for example, okay, the change in equilibrium, let's say they say this equilibrium system, we disturb by increasing the pressure. So what we need to do is we need to, according to Le Chatelier's principle, you need to bring down the pressure. How do you bring down the pressure? By shifting the position of the equilibrium to less number of molecules. So you just mentioned that the position of the equilibrium will be shifted to the right and to favor less number of molecules. Okay, less number of molecules. So in that process, you need to mention that A is going to, concentration of A will decrease, concentration of B will decrease. Okay, solid, if you don't want to mention, because solid, no need to actually mention. So D, we can actually mention the concentration of D is going to increase. Okay, so concentration of solid is going to be constant. So we don't include that. So this is going to be, I have mentioned about temperature, I have mentioned about concentration, I have mentioned about pressure. All these will affect the position of the equilibrium. But do remember, we have this concept, what we call as Kc and Kp. Kc and Kp, we know how to actually write down. They are called equilibrium constant. Now, this equilibrium constant, okay, please remember the equilibrium constant is only affected by change in temperature only. Okay, by temperature only. So you need to remember that Kc and Kp, they are not affected by change in concentration. They are not affected by change in pressure. And again, if you are using catalyst, they are not also going to be affected as well. Okay, so Kp and Kc are only affected by temperature. Very, very, very important. Okay, now, so the once we have done that, okay, we have learned about this acid and base equilibria. Now, acid and base equilibria is very important because we have learned about, okay, what when we have, for example, Bronsted Lowry. Okay, according to this Bronsted Lowry, we can define acid as a proton donor, and we can define base as a proton acceptor. Now, so if, let's say, if I have, okay, an equation like, for example, ammonium reacting with water to give you ammonium ion plus OH minus, okay. So we know that, okay, water is actually donating the proton, and therefore, okay, water can be actually represented as acid because water is going to be a proton donor. Okay, it's a proton donor. because ammonia is accepting the proton, okay, to become ammonium ion, so they become the base. So very important also, if you have ammonia changing into ammonium, so ammonium, we need to know that ammonium is conjugate acid. Okay, it's going to be the other way around. Base, then it become conjugate acid. So this water will give you OH minus. So therefore, this is going to be known as conjugate base. Okay, do remember that. In this chapter also, we have learned that, okay, we have strong acid, we have strong base. We also have learned that we have weak acid and weak base. So how do we define all that? Okay, strong acid completely dissociated, okay, or completely ionized. Okay, the same. Okay, completely dissociated in water, completely dissociated. Strong base also completely dissociated. But weak acid and weak base are partially dissociated or partially ionized. Okay, so that is going to be the partially dissociated and partially ionized. Okay, so that is going to be the definition. Okay, how do we define strong acid and strong base? Not based on pH. So please remember that. Okay, we define strong acid and strong base, or weak acid and weak base, based on how better that they can actually dissociate. Okay, that is very important. And then over here also we have learned about, I think if you look at overall, if this is base, okay, base, and then alkali. Alkali is just a special kind of base where they can dissolve in water. Okay, so that is going to be alkali. So example of alkali: sodium hydroxide, potassium hydroxide, and I told you ammonia is also alkali, okay, because they dissolve in water also. Okay, so I hope you can understand this entire chapter, okay, and how to apply. I think the most important part is going to be the beginning part, but of course for the conjugate acid and conjugate base, there's also a very important concept that you need to know. Okay, that's it for today.